Hey there, welcome back. Welcome back to the channel. Welcome back to the CSES problem solving sessions. And we have solved a couple of problems of graph algorithms in CSES set. And today, in this video, we'll be solving the next problem in the same set. And the problem name is building teams. So I think this problem is here building teams, right? So this problem is nothing but bipartite graph problem. So if you have ever solved a bipartite graph problem, maybe you don't need to solve it, or you can just try. You can just look and just ask yourself if you will be able to write a working solution for it or not. If you have any doubts in that, then you should try it. You should start writing the code from scratch and try to submit if your solution works or not. Now this problem is very important, and you may get this problem as a warm-up problem in many interviews. And so if you haven't solved this problem before, then this problem is worth solving. So without wasting any more time, let's jump to the problem solving thing. Hey there, welcome back to the channel. So let's continue solving the problems. So the next problem is building teams. So in this problem we have n pupils in Olivia's class. So pupils here do not mean the pupil rating on code courses. N pupils means n students, and there are like m friendships between those students. Your task is to divide the pupils into two teams in such a way that no two pupils in a team are friends. So people who are present in one team, no two of them should be friend of each other, right? If there are two friends, then both of those friends must belong to two different groups or teams. Okay. Now let's solve this thing. So let's divide this thing. Let's say we have now we have this example. So we have 5 people and 3 friendships between them. So there is a friendship between 1 and 2. So I represented it like this. There is a friendship between 1 and 3. There is a friendship between 4 and 5. Now these are two-way friendships. Like friendship means two-way thing. Friendship is a two-way thing. A is a friend of B. B has to be a friend of A. Okay. It has to be a two-way thing. Why I'm emphasizing on this point? Because you people must be able to identify the directed and undirected graph. You should be able to differentiate between the directed and undirected graph. Undirected graph means the edge between any two nodes is two-way. So I can move from A to B and from B to A. That is an undirected edge, while a directed edge is like I can move from A to B only. Okay. So here I'll model this problem as a graph problem where we have 5 nodes and 3 edges. So the first edge is between 1 and 2, then there is an edge between 1 and 3, then the last edge is between 4 and 5. So let's divide these nodes into two teams. So the purpose in this problem is to divide these n nodes into two parts or two teams or two groups such that there is no edge between any two members of the same group, right? If there is an edge, then the nodes of which are present at the end point of that edge must belong to different groups, right? So how we can ensure it? So let's start with node number 1. So let's mark it green and put it in group 1. Let's put node number 1 in group 1. Now I can't put node 2 and node 3 in the same group where I put node number 1. Why? Because there is a direct relationship between 1 2 and 1 3. Like there is an edge, and we can't have two nodes in the same group where having edge between them. So 2 has to be put in the group 2. So let's mark it as red. So this is present in group 2. 3 is also in group 2. Let's mark it as red. Now let's move. Now 2 has been put to one of the groups. 3 has been pushed into one of the groups. Now let's move to 4. Now 4 I can put in any group. So let's put it in group number 1. So let's put 4 here and mark it as green. I can also put it in group 2. Why? Because there is no edge between 3, 2 and 4, and also there is no edge between 1 and 4. So I can put 4 in any of the two groups. But since I have put 4 in group 1, now 5 has to go in the different group. So 5 has to go in group 2. So this is a possible partition. This is one of the possible answers for this particular configuration of nodes. That means I put node number 1 and node number 4 in group 1, and I put node 2, 3 and 5 in group 2, right? Is that clear? Yes. So that's all we have to do. So how the answer will look like to this problem? The answer will look like an array where the array of n elements. So for element number 1, that means node number 1, I'll have to mention whether it is in group 1 or 2. Since here 1 is in group 1, so I'll print 1 for node number 1. For node number 2, I'm going to print 2 because 2 is present in group 2. For 3, again 2 because 3 is also present in group 3. For 4, I'm going to print 1 because 4 is present in group 1. 5 is present in group 2. So for 5, I'm going to print 2. So this is the answer. This is the answer. This is the answer that we have. Now this is the groups array that we have. Now there are some cases where I'm not able to divide the nodes into two groups. Let's take this example here. This example 3 and 2. So there is a direct edge between 3 and 2. Now since there is a direct edge between 3 and 2, they must be put in separate groups. But here both of them are colored red, means both of them are present in the same group. So one has to be removed from the group 2. So let's say I remove 3. Now where would I put 3? I can't put 3 in group 1 either. Why? Because 1 is present there and there is a directed edge. There is a direct edge between 1 and 3. So I can't put 3 in group 1 as well. So I will need one more group for 3, but that is not possible. We have only 2 groups, and hence there is no solution for this type of arrangement of nodes. So for this type of arrangement, I am going to print impossible in capital letters. Impossible in capital letters. Okay. There are some things which are not possible. This is one of them. So I am going to print impossible for that. So now what we can do here? What we can do here? Anything? How would you solve this problem? Let's see. How would you solve that problem? So to solve this problem, all we need is to just run a DFS from node number 1. So run DFS from node number 1. Color it as green. Let's represent green color by 1 and red color by 2. So I am having this red color, and so push 1 into group 1 and push 2 into group 2. From 2 I can't move anywhere else, so I'll come back. So 1 and 2 are in separate groups, so I have pushed 1 in group 1 and 2 in group 2, right? Now from DFS 2 I'm gonna come back to DFS 1, and from DFS 1 I'm gonna move to DFS 3. I'm gonna move to DFS 3. So let's move to DFS 3, and here I'm gonna color it with 2, color number 2, right? Now from here, from node number 3, I can't move to node number 1, so I'll move back. Now 3 is pushed into group 2, so 3 is here. From here, move to node number 1. Now 1 is visited, 2 is there, 3 is visited. Let's go to 4. Let's go to 4. Let's go to 4 and color it as 1. So let's put you know what we're gonna put. We're gonna put 4 in group 1. Now also move to 5 and color it as 2. So push 5 in group 2. Is that fine? 1 4 in group 1 and 2 3 5 in group 2. Two, 3, 5 is in group 2, 1, 4 is in group 1. I think it's clear. 1, 2, 3 is in group 1 and 4, 5 is in group. No, 4, 5 should not be there. 1, 4 is in group 1 and 2, 3, 5 is in group 2. So in this fashion, I'm gonna group these elements. So whenever I'm moving from node A to node B, I'm gonna change the color. So I'm gonna alternate over the color. It's like 1 2 1 2 1, and while also ensuring that no two adjacent nodes gets the same color. That I also have to ensure. So let's say, how would you handle if there is a direct edge between 3 and 2? How you gonna handle it? Let's see. Now you move from 1 to 2 here, and now from 2 you move to 3. So let's erase this particular left subtree. And now from DFS 2 you move to DFS 3, right? And you color it with 1. So now this 1 is green, 2 is red, and now 3 is also green. 3 is also green. Okay. Now from 3 I can't move anywhere. I move back to 2. Then from 2 I move back to 1. Now from 1 I visit the second neighbor, which is 3. Now when I'm visiting this second neighbor, I see that I'll have to make this check that 3 is already visited through this particular way, 1 2 3. But I will check when I'm moving to the second neighbors, it is visited. Now I'm gonna add another check that whether 1 and 3 have the same color or not. If they have the same color, means it is not possible to fit 1, and it is not possible if they have same color, then the answer is simple no. Why? Because the neighbor node has been colored green through some other way. But if I move from this way through this way, this has to be colored red. This has to be put in another group, but it is already pushed into the same group where 1 is present. So that means there is a problem. We can't partition the nodes. So we're gonna return false right from here. So once I return false right from here, the whole thing collapses, and we simply claim that we have no possible or valid solution for the problem, for the graph. So all you need is a single false, like this type of condition, in order to make the entire thing say that there is no possible partition, right? And if you do not find any such condition while you traverse through the graph in its entirety, means there is a way to partition it. And just keep going alternatively, keep changing the color while you move from one node to another node, and that's all, like I'm doing here, from 1 to 2, then from 2 to 1, then from 1 to 2, 1 to 1 to, like this. So that's all. It can be solved using a simple depth first search strategy. So let's try to implement it. So we have recorded the graph, we have the groups array, we have the visited array, and now let's iterate over each node and start assigning the node a group. If any node is not visited, that means I haven't visited it yet. Let's put it into group 1 and start a DFS from here. So put it in group 1 and start a DFS. Now this DFS returns a boolean value, either false or true. If it returns false, means there is no valid partition. If it returns true, that means there is a valid partition. So if it is returning false, I'm going to print impossible right here, and I'm going to return right from here. If it does not return false for any node, that means there was a valid partition which has been recorded in this groups array. That's why I created this group array. Now my task is to simply implement this DFS function. It's not, it's bool DFS node. Here we have the color, here we have the group is nothing, group is a vector, it's a vector. Then we have a vector for visited array, boolean vector. Then we have a graph, and here you mark the visited for the node to be true, and then you also assign the group to the node as G. Now you iterate over the neighbor node, and if you find the neighbor to be not visited, then what you're gonna do is, since the neighbor is not visited, simply visit it, call DFS. And now, since I'm moving to the neighbor, I'll have to change the value of G. I'm moving to the neighbor. If the G is 1, it will become 2. If G is 2, it will become 1. So for that I'll use an equation like 3 minus G. So if G is 1, 3 minus 1 becomes 2. If G is 2, 3 minus 2 becomes 1. So it will simply assign the right group to the neighbor node and pass everything else as it is, visited and the adjacency matrix, adjacency list. And now since this returns true and false, what you're gonna do, since if it returns false, you will return false right from here. If it returns false, otherwise if the node is visited, then what you're gonna do, if the node is visited, then what you will do, if it is visited, you will check the color of the node or the group of the node with the group of the neighbor, and if they are same, then you're going to return false, otherwise you will return true. Now here I'm going to print the group array. Since I was able to perform the grouping successfully, I'm going to print this group array. This will work, I think. Let's check. A plain DFS 12212. Let's try to submit it. Now this problem is nothing but a bipartite graph. If you have solved this before, you may have an idea how to solve this. Okay. Standard problem, got accepted, and that's all for this video. What's time complexity for this? Since we are using depth first search, time complexity would be big O of n plus m. The space complexity will be big O of n. Why? Because we have a call stack and we also using this neighbors, this group array, right? I hope it makes sense to you people, and we haven't used any fancy algorithm so far. Just we are solving problems using DFS and BFS, and I'm sure you are able to get the solutions. You are able to solve some problems. And the next video we're going to be solving this round trip. This is also an easy one, and till then you try this problem on your own and try to solve this using BFS. So I solved it using DFS. Try to solve it using BFS. And I'll see you in the next video. Till then, take care, bye bye, and keep solving problems. Okay. So this game is like, you can't, it's not like how I'm able to use this type of technique, why I called this DFS and how it just came in my mind. So many students ask this. This is because of experience. I have solved this problem and similar problems a lot of times. Actually, I have solved more than 3,000 problems, so 3,000 to 4,000 problems over various coding platforms. At least if not much, I think 3,000 account is there. Yeah, I think I have solved 3,000 problems. Yes, and I am doing this thing for the last 5 years. I am doing it. It's been 5 years. I'm consistently in touch with the data structures and algorithms, and maybe that simply because of the experience I am able to solve these problems. It's not because of I'm more brilliant than you or anything else. like this thing is like if you are brilliant, then you will be very good in the craft in a very short span of time. Unlike my case, I became good at it when I practiced this thing for a long time. Some people become good at it in a very short time, like 6 months or 1 year, because maybe they are better at mathematics, they are better at solving puzzles, they have a better background means they are like they may be like giving those mathematical exams, olympiads, from the very young age. NTSC, IT, IMO, I think, I don't know what is it, I don't know. So maybe they are involved in these things from a very young age, so the mental patterns develop slowly and slowly. So people who are who crack JE with really really good rank, the chances are more that they become better at this thing in a very short span of time. So this is that doesn't mean that you people can't be better. Of course there are cases where people from not so people with not very good JEE rank got good at it, got really really good at it. Now that is your brilliance, your efforts, how consistent you are. If you are if you are solving at if you are solving every single day, your own resilience, etc etc etc, discipline, जो भी है. But what I understand from this is you have to give time. If you want to, even if you are really not very smart, like I was very slow in this thing, I was not a, I don't have that good background in solving problems, mathematics, things like that. But I just gave it a lot of time, so I became good at it. So that's all you have to do, you know. Don't overthink, just keep giving it time for a long period of time, and you will be able to solve problems one day. Okay, so that's all for this video. I'll see you in the next one. Till then, take care. Bye bye, ladies and gentlemen.